Okay, so as I mentioned, we're going to be recording this session because this is a session where we're going to be doing some problems relating to electrical charge and Coulomb's law. If anybody has any objection with the recording of the session, you may say so now. You may turn off your cameras if you wish, or leave them on. Okay, so we're going to be basically this set of problems. The purpose of this set of problems was for us to be able to familiarize ourselves with the use of Coulomb's law, and also to kind of understand the dynamics that occur between charged particles and electrons, protons, and try to also relate these to remember what we're calling Leonardo's uh, con- uh, uh, controversy, or Leonardo's conspiracy theory between Newton and Coulomb. Try to relate this a little bit to Coulomb's law and Newton's law. One has to do with forces with that are electrical charges. The other one has to do with forces that are related to gravitational um, fields or phenomena. And both of the expressions of these laws are very similar in their structure. They are proportional to the magnitudes and inversely proportional to the square of the distances. Okay, so let's start off with problem number one, which was from the clerks of Maxwell.
Yes. Do we share the screen?
Yes, let me stop sharing here. So let me just, before we share the screen, we're going to go with problem one. Let me just stop sharing. Do you have the definition of the problem in your document, or should I show it?
Yes, we have it.
You have it? Perfect. Then go ahead.
Okay, it's that one.
Okay, so this is problem one. It says two charged spheres 10 centimeters apart attract each other with a force of 3.3 times 10 to this is supposed to be a negative 6 newtons. What force results from each of the following changes considered separately? Both charges are doubled and the distance, okay, A, both charges are doubled and the distance remains the same. So I did like a mini sketch, I didn't know how to do like a free body diagram, but I think that because there wasn't like any push or pull, so I just added the little electrons. So it says that both charges are doubled and the distance remain the same. So if the first one and the second one is doubled, you add them, so you multiply the forces by 4, so you could quadruple the force. And there's a in the reading on top of there was a reading and then there were the questions. There was a law that stated that if both forces are double, we have to quadruple the force. So it's 4 times 3 times 10 to the negative 6, and the answer is 1.2 times 10 to the negative 5 newtons.
Okay, good. I just want to make two quick comments here. One is please make the correction of the -6 on the PowerPoint, because I'm going to be taking these slides and including them into the main unit one PowerPoint, and so these are references for you guys. So add that, please. By the way, very good presentation. By the way this looks. By the way, so congratulations on that. I just want to make a quick comment on what you're saying, Lucia, which is correct. By the way, the force is quadrupled. Okay, but I'd like for us to take a moment, just again, because this is the basis for stuff that you guys are going to be studying, just to understand why the force is quadrupled. And yes, it could be stated as a law. If we duplicate the charges, the force is quadrupled. But let's understand why. Remember that we have Coulomb's law, okay? And Coulomb's law says that we have constant K multiplied by charge 1 charge 2 divided by the square root of the distance, right? Now, what happens if I suddenly double the charges? Well, let's call this force 1, okay? Force 2, which is going to be the new force once the charges are doubled. I'm going to call this force 2. I'll write it down here. Force 2 is going to be K. And now Q1 is going to be the double, or is going to be doubled. So we're going to have 2 Q1. And we're going to have the double of Q2. Okay? And this is divided by R squared. Does everybody see that? And so F2, because of this, F2, which is the new force because we've doubled it, is going to be 2 times 2 is going to be 4. And the rest of the expression, K Q1 Q2 divided by R squared. Okay? And so what do we notice between F1 and F2? Well, we notice that F2, well, this part here is F1. And so that means that F2 is 4 times F1. Okay? Is that clear to everybody? And it's basically what Lucia was saying. So if the charges are doubled, then the force is going to be quadrupled. That's kind of just the mathematical explanation of where that comes from. Okay? Is that clear to everybody? And Lucia also and first team, where that came from?
Yes.
Yes.
Okay, good. Again, everything, this is being recorded, so I'm going to clear these drawings, okay? Sorry for the interruption, Lucia, please, I'm going to erase the drawings, okay? Please continue.
Okay, so number 2, it says an uncharged identical sphere is touched to one of the spheres and then taken far away. So I put that the yellow was uncharged, it touched, and then it's taken away to another direction. So if a charged sphere touches an uncharged sphere, it will take half of its electrons. It will take half of its excessive electrons. So we divide the force by the half because, well, how we divide the force by half, and it will give us the new force, and it's 1.5 times 10 to the negative 6 newtons. And
Okay,
there was
good.
also a law there on the reading that said the one of the Newtons. It's no, sorry. No, yes, Newton's law. There was one that said that you should divide by 2.
Okay, perfect, very, very well. Lucia, before we go to the next one, let's just talk a little bit about this. I'm going to maybe leave this here. So again, we've got the original situation, which is F1, which is 2 charges, Q1 and Q2, R squared. Okay. Now, what Lucia just explained is that we have an uncharged identical field, an uncharged sphere. And then we grab the sphere that's charged and touch it to it. So the sphere has charge, let's call it Q1. And then I have an uncharged field and I touch both of them. So remember, all systems try to balance themselves. So if I have one charge Q1 and another object or another sphere that doesn't have any charge and I touch them, the charges are going to try to balance themselves out. So the sphere that didn't have a charge now is going to have half the original charge, okay? And then I took that one away and I placed the charge again next to the other one. So what is that going to generate? Now we're going to have a force 2 that's going to be K. And instead of having Q1, now I'm going to have Q1 divided by 2 multiplied by Q2. And all of this is divided by R squared. This in the end is going to give me K Q1 Q2 divided by 2 times R squared. And what do we notice here? Similar to the other problem, this is this. Okay, and so what is the relationship between F1 and F2? Well, F2 is 1/2 of F1. Okay, that's where the 1/2 comes from. Okay, so very good. Questions here with this one. Is that clear to everybody also? Okay, good. I'm going to, if there are any questions, I'm going to clear this again, and please continue, Lucia.
Okay, so the last one, it says the separation is increased to 30 centimeters. So we have our two electrons and our 30 centimeters. So first, if we know the formula, like we already have the force, we just have 2 divided by the 37 centimeters square, which is 9 meters, and the answer is 3.3 times 10 to the negative 7 newtons. And so F is reduced by 1/9.
Correct. And this also happens because in the formula, remember that we've got the division of the square, okay? Of the square of the distance. So if we increase, the original distance was 10 centimeters. So now we are, the new one is going to be 1 divided by 3 times R elevated to the square. This is going to give us 1 divided by 9, which is what Lucia, or 1 divided by 9R, which is what squared, which is what Lucia is saying. In this case, if we triple the distance, then the force is going to be reduced by 1/9. If we duplicate the distance, the force would be reduced by 1/4, and so on and so forth. Okay? Remember that the force is going to be inversely proportional to the square of the distance. Okay, so it's logical to say that the force is going to be reduced. Okay, very well done. Again, very good presentation. So please just correct the -6 here on the PowerPoint, so you guys can so I can add it to the slides. Okay.
Okay. Do we like share all of our problems, or are we going to like be changing for?
No, we're going to be going in order because the level of the problems kind of increases. So we're good with number 1. Now we're going to go with number 2. Very good presentation, by the way. When I say presentation, the way it looks, very good. So correct that, please. And in this particular case, yeah, you can turn it in as a PDF or a PowerPoint as you wish. I just need to be able to take a screenshot of the slide so I can include it in the main PowerPoint. Okay, perfect. So well done with that first one. Thank you, Lucia. Let's go with team house 2, which is Pichita's No Mercy. Go ahead.
Yeah, so problem number 2 is the force of electrostatic repulsion between two small positively charged objects A and B is 3.6 times 10 to the third power when AB equals 0.12 meters. The question is, what is the force of repulsion if AB is increased to 0.24 meters and B 0.36 meters? We know by given by the formula, which is Fe, the little circle, well, the little a, I don't know how does it stand for, and which is 1 divided by d squared, which states that if we double the distance between charges, we quarter the force. It's almost the same as the problem number 1. If divided the distance by charges, we multiply the force. So in problem A, it was double the distance and multiply by 1/4. So we did the equation, which is 1/4 times 3.6 times 10 to the fifth power, giving us the answer of 9 times, well, I put the letter E instead of the 10th, minus 6. And for problem number B, I triple the distance and then multiply by 1/9, reducing the force, which is 1/9 times 3.6 times 10 to the fifth power, which will give us 4 to the 10th power minus 6.
Okay. Good. So this is the same principle as that we mentioned in the previous problem. So since we're working with the inverse of the square of the distance, if we duplicate the distance, the force is reduced by decreased by 1/4. If we triple the distance by 1/9, if we were to make it 4 times larger, it would be 1/16, and so on and so forth. Just some observations here for all teams. So you guys are using PowerPoint, right? So the format is PowerPoint?
Yes.
Okay. I'm going to ask all teams to do this, and just because it's a thing that you guys should be able to know how to do. I want all of the problems to have a congruent format with regards to the expression. So here, for example, the force is also 3.6 times 10 to the minus 5. Okay. So imagine again that I'm going to take a screenshot of this, and everything should be clear for everybody. So please correct that. And if you're using PowerPoint, there's a formula editor where you can add a formula to the PowerPoint. Okay. Please use that to represent the expression, so it's not confusing. Okay. So please correct this one also. Okay. This goes for all teams. Okay. The other thing is, by the way, I applaud at least these first 2 teams that are doing this in PowerPoint. I didn't necessarily expect you to do it in PowerPoint. You could have actually solved it by hand as long as it was clear, and take a picture of that also. But if you are doing it in PowerPoint, then please do the corrections so all the expressions are congruent and understandable. Okay.
Okay. Thank you.
Okay, but well done. Questions with this one? No. Okay, good. Thank you very much. Let's go with team House Delta Sigma, and you guys have problem number 3. Perfect. Actually, before you begin, you could actually have done this also. Okay, that's fine. In the end, what I want is that I want to be able to take these again and put them in the main PowerPoint, so you have all of the problems solved. Okay, so this is also completely valid. Okay, as long as the writing and the procedure is clear. So please go ahead.
So problem number 3 says calculate the force between charges of 5 times 10 to the negative 8 and 1 times 10 to the negative 7 coulombs if they are 5 centimeters apart. So this problem basically is just substitute all the data that the problem gives us, and it's 9, the formula is 9 times 10 to the 9 times Q1 times 2 Q2 over 0.05 meters to the second power, and the answer is 0.018 newtons.
Correct. Well done. Just one very slight observation. In the case of these problems, it recommended to use the 8.99 instead of the 9. It really doesn't matter if you use the 9. The difference isn't going to be that large. It's not a problem if you guys use the 9 times 10 to the 9. Okay. Some problems are going to specify the 8.99, but it's really a very minute difference. So this is just a direct application of Coulomb's law. Okay, good, well done. Okay, let's go with, we've got electric bakers, problem 4. Please go ahead, electric bakers. Okay, there we go, Pedro.
Well,
Or Diana, I'm sorry.
Carmina.
I'm sorry, Carmina. I'm sorry. Remember one thing, please. When you're going to participate, turn on your cameras, because when I'm screen sharing, and you're going to see it in the video, the only thing I've got is the bar where I can only see 3 or 4 people. So when one of you participates, I can't necessarily see who's speaking. So apologies if I mention a different name. So sorry, Carmina. Go ahead.
Yeah. This is also a simple one that says, what is the magnitude of the force? A 1.5 times 10 to the negative 6. Coulomb's charge exerts on a 3.2 times to 10 to the negative 4 coulombs charge located on 1.5 meters away. So we substitute and we use the constant the K, and you said that we should use the 8.999, but we use the 9. And so we multiply 9 times 10 to the 9 times Q1 times 2Q divided by R, which is 1.5 to square, and that gives us 1.92 newtons.
Okay, good. Well done. Thank you, Carmina. By the way, this is another way talking about the. Oh, could you please leave it there, Carmina? Don't
It was
remove
Pedro.
the. I'm sorry. Okay, whoever's showing. Please don't remove the screen sharing until we're finished, or I'll let you know. Thank you. By the way, this is another way of doing the format, which is very good. So what I think you guys did here is that you kind of copy pasted the image of the 1.5 times 10 to the minus 6 coulombs instead of having to write it down. That's fine.
I wrote the formulas in Word, and then I screenshotted and paste the image.
So you did them in Word with the formula editor?
Yes.
Oh, perfect. By the way, remember that the formula edit, that's a good way of doing it also, because sometimes it's easier to work in Word than in PowerPoint. But you can also add formulas in PowerPoint with the same formula editor if you want. But this looks good, okay? Because the procedure is clear and you're using the expressions, and this is what I was talking about, that if we look at the problem, we should understand everything. Remember also to always put the units, okay? So this also has coulombs, meters. This is very well done. Okay, so good job, electric bakers. Okay, now you can remove the screen sharing. Thank you. Let's go with Pivana. How's Pivana?
Let me share my screen.
Hmm?
So the problem says 2 spheres that are 4 centimeters apart attract each other with a force of 1.2 to the 9 newtons. And we have to determine the magnitude of the charges like on both ends, knowing that one has twice the charge as the other one. And for this problem, we just substitute the q's with x and 2x, and we just do the regular formula and solve for x. So yeah, this is the formula. We use the normal force formula, and with that we just solved for x by how do you say this? By using the square root and then dividing by 2. And after that, we just substituted those answers again in the formula. So we could make sure that the answer was correct. And it gave us 1.03 to the minus 11 coulombs and 2.06 to the minus 11 coulombs. And the answers that were on the document were rounded. They were 1 to the minus 11th and 2 to the minus 11th.
Correct. Very, very well done. Thank you, Diana. So basically, again, this is the application of Coulomb's law, and basically, one charge is Q, the other is 2 times that. So we just solve for Q, and also the document has all the answers at the end, like Diana is mentioning. All the answers are rounded up. I noticed that also. But the idea for you to have the answers there is for you guys to be able to verify your calculations. Okay, so well done. So up until now, we're talking about problems that are helping us practice or relating Coulomb's law. Okay, we're going to start adding some additional things to these in the next set of problems. So well done. Now let's go back to the clerks of Maxwell. Oh, and by the way, all of you guys worked on your logos and all that. So when you're doing a presentation, include your. Oh, you did. That's in the cover page. Perfect, perfect. I really like the logos. Again, I'm right now. I'm in a very Call of Duty thing. So when I look at the logos, I remember the emblems and things that you can get when you get points. So remember to include them. So good there. Let's go with number 6 then. Clerks of Maxwell.
Okay, so problem number 6 states that 2 equal charges of magnitude 1.1 times 10 to the negative 7 coulombs experience an electrostatic force of 4.2 times 10 to the negative 4 newtons. How far apart are the centers of the 2 charges? So first of all, the original formula, we substitute the values and we find out that the only missing value is the distance. So we gotta clear everything but the distance. So we pass the distance to next to the force, and we by multiplying, and we get rid of the force by dividing. And to get rid of the square, we just pass it as a square root. And finally, we got the square root of the constant times the 2 charges divided by the force. And finally, we get the result that is 0.509 meters.
Correct. Well done. Again, we're practicing Coulomb's law here. The other important thing to mention here, we mentioned it before, but just to make it clear, because we're going to be referring to this in the next topics, is that remember that we're talking about what are called point charges. Okay, so it's 2 charges that represent points in space and are separated by a certain distance. Okay. Now, it's important to note that when in all of these problems, we're talking about point charges. So notice that in some problems, they say there's a sphere that's charged, and the distance between the center of the sphere and the center of another sphere or any sort of object, we're considering that all objects are points in space. Right now, they don't have any sort of volume. Okay. We are going to talk about how electrical fields behave for objects that have a certain volume. And that's one of the next topics we're going to see. And we're going to talk a little bit about Gauss's law there. But right now we're talking about points in space that have no volume. So we're considering all of these with those characteristics. Okay. Very well. Well done, clerks of Maxwell. Let's go with problem number 7 with Bichita's No Mercy.
JC.
In problem number 7, we were asked how many electrons must we remove from a neutral isolated conducting sphere to give it a positive charge of 8 times 10 to the negative 10 to the negative 8 coulombs. No, yes, coulombs. Yes, that's coulombs. Okay, so if it's neutral, then we have to take away some electrons because they have a negative charge in order to have the positive charge that we desire. So how do we do that? We divide the 8 times the 10 to the negative 8 by the coefficient of the electrons, which is, I put it on top, 1.602 times 10 to the negative 19. When we divide it, we have the answer of 5 times 10 to the negative 11 electrons.
Okay, it's 5 times 10 to the 11, not negative 11.
Okay, I said negatives, I'm sorry.
Yeah, it's 5 times, so it's a lot of electrons that need to be removed to be able to generate that charge.
And it's not a big charge. It's a 10 times 10 to the negative 8, but the electrons have a very small coefficient, so we need a lot of them to create that kind of positive charge.
Exactly. That's the takeaway. So remember that when we're talking about charges, we're going to be using small values. So usually coulombs are going to be in microcoulombs, or nanocoulombs are going to be in small units. But the charge of 1 electron is a very, very small charge. So basically, we remember that we don't measure charge with regards to the amount of electrons. We measure charge with units called coulombs. So a charge is generated when we remove or add electrons to any sort of matter. But we don't measure that charge in electrons. We measure them in coulombs. So if I have, if I want a sphere to have a positive charge of 8 times 10 to the minus 8 coulombs, and to generate a positive charge, we would need to remove electrons. So how many electrons should I remove? Well, 1 electron has a charge of 1.602 times 10 to the minus 19. So how many of those charges can fit into 8 times 10 to the minus 8? And so basically we do a division there. And we get that it's 5 times 10 to the 11 electrons. So that's a lot of electrons that need to be removed because of what Jose Carlos was mentioning about the very small amount of charge of an electron. Okay, so well done. Just one observation. Okay, this has nothing to do with electricity and magnetism. And remember, and this is being recorded. Okay, so remember, whenever I make a comment, a critique, okay, it's a critique to try to make you guys better, always. So one thing that I'm going to recommend when you are doing any sort of team presentation, we're going to follow the rule, the phrase that says there's no I in team. Remember that there's no I in team. So whenever we're explaining something or writing something down and it's a team presentation, we're not going to say I found the answer of this. Okay, we're going to say we found it. Okay, it's just a recommendation I'm giving you guys. Okay, whenever we're in a team, and this is kind of my philosophy, whenever we're in a team, we should always present ourselves as a team. Okay, but well done, you guys. Questions with problem number 7. Okay, problem number 7 is one of those very simple problems, but you kind of have to think about it. Kind of wrap yourself around it in the concepts that we're talking about. Okay, questions with problem number 7? Nope.
No.
Okay, good. Well done, Jose Carlos. Okay, let's go with. I think we can go with problem number 8 before we go to break. We're almost halfway there.
So the problem number 8 states, what will be the force of electric repulsion between 2 small spheres placed 1 meter apart if each has a deficit of 10 to 8 electrons. Well, an electron has a constant value that is 1.6 to the minus 19. And if it has a deficit of 10 to the 8, we just subtract those values and we'll have that is 1.6 elevated to a minus 11. So we already have the constant, which is K, that is 9.9 to elevated to a 9. And we have the 1.6, and we just divide it by the distance, that is 1 meter. And we got that is 2.204 elevated to a minus 12.
Okay, very well done. I just want to clear something up here, just so we don't have any sort of confusion, okay? Because you said something, Alejandro, that's correct, but is could very easily be misinterpreted, okay? So I just want to clear that up. It says that we're trying to find the charge of the sphere, okay? And this charge of the sphere, I'm going to call it Q1, is going to be a charge that's generated by removing 10 to the 8 electrons. So I know that the charge of one electron is 1.602 times 10 to the minus 19. This is the charge of one electron, okay? But it says that we have 10 to the 8 electrons. That means that I'm going to multiply this by 1 times 10 to the 8. Okay? I'm multiplying it. I'm not subtracting it, because you mentioned subtraction. Now, why the subtraction? Because mathematically what's occurring is that the exponentials are subtracting in this multiplication. So Q1, which is the charge, is going to be 1.602 multiplied by 1 is 1.602 times 10, and by the laws of the exponents, minus 19 multiplied by, or 10 to the minus 19 multiplied by 10 to the 8, the exponents are going to subtract. So that's what gives us the 10 to the minus 11, okay? So it's not that we're subtracting, it's that mathematically the multiplication is generating the subtraction of the electrons. And in this case, both charges are going to be the same, so Q1 is going to be equal to Q2, okay? Questions with this one before we go to break? Nope?
No question.
Okay, good. We are going to take a 10-minute break. I'm going to pause recording and we'll be back with the rest of the problems. Thank you. Okay, we are back and we're going to continue with problem number, I think we were in problem number
9.
9, right? 9, electric bakers.
Okay, so here we have the problem number 9. It says two identical small spheres of mass of 2 grams are fastened to the ends of a 0.60 meter long light flexible insulating fishing line. The fishing line is suspended by a hook in the ceiling at its exact center. The spheres are each given an identical electric charge. They are in static equilibrium with an angle of 30 degrees between the strings halves as shown. So we need to calculate the magnitude of the charge in each sphere. So first, I calculated the distance between the two spheres. So in order to do that, sorry?
Remember what?
Yeah, sorry.
I'm just gonna be. I'm sorry. I'm just gonna be. I wanted to. I just wanted to kind of make you guys remember that, again, when you're doing a team presentation, and remember that you might have to be doing this in other settings that aren't necessarily academic settings, okay? So whenever we're presenting as a team, always try to remember to say we, okay? And you're not gonna flunk the course if you said I. I'm just trying to make you guys think about that. So sorry about that, Karen.
Yeah,
Please go ahead.
So we calculated the distance between the two spheres, and in order to do that, we separated the triangle into two triángulos rectángulos. How do you say that in English?
Two rectangles, triangles, that's fine.
Oh,
Or
okay.
two straight triangles.
So yeah, so we used, in order to find the measurement of B, we used the sign of 15 multiplied by the measurement of C, and we have, that gave us a distance of 0.077 meters. So the total distance will be that distance multiplied by 2. So the radius will be 0.15 meters.
And let me just correct myself here, because I said something incorrectly. It's we're talking about right triangles. Okay, it's a
Okay.
right triangle. I'm sorry about that. I said something else. It's right triangle. Huh?
Yeah,
That's
okay.
correct. The procedure is correct.
Thank you. So, oh, sorry. Sorry, they were knocking at the door.
No worries. It happens everywhere. Don't worry.
Okay, so then we divided the components into y and x of the forces in order to find the force that we needed for the formula to get the magnitudes on each sphere. So we divided into y and x components, and we calculated the y component, then, which is force equals to mass times gravity, and we got a 0.0196 newtons, and then we calculate the x component, which gave us a 5.25 times 10 by the minus 3 newtons, and that would be the value for the force due to equilibrium, because the problem mentioned that it was in equilibrium. So then, now that we had the radius and the force, we just needed to substitute in the formula. And since we have the same values on each charge of the spheres, we used q to the square, and it gave us a total of 1.14 times 10 to the minus 7 coulombs.
Okay, let me just make some observations here. That is a bit of a difference. So in the answer, it's 1.2.
Yeah.
And let's just verify a few things here. Okay. And if you want, leave that slide there. Okay. I may have to verify some of the calculations here. Okay. One thing that I'm going to ask you guys to do in these problems, please, is to remember to try to do a free body diagram, just so we're very clear about the forces and where they're at and how they're directed and the signs and all that. Okay, so so don't move the slide because I'm gonna draw here. I'm gonna place myself here in this charge, and I'm gonna do a free body diagram. So we're gonna have a free body diagram there on the charge. Okay. And by doing the free body diagram, let's identify the forces that are interacting here. Okay. And so there's going to be, both charges are of the same value. Okay. Both charges are not only of the same value, they are also of the same sign. We don't know if they're negative, or do we? No. They just said that they're given an identical electrical charge, We don't know if it's positive or negative, but if the two charges are identical, that means that there's a repulsion force, okay? So that repulsion force, I'm going to draw that here in purple. Oops. That repulsion force is going to be going this way, okay? And this repulsion force is going to be the force, I'm going to call this F Q, is given by Coulomb's law. Okay, are we clear up to that point? What other forces are interacting here? Well, like Karen mentioned, there's also a force due to gravity. So there's another force here that is going to be the force of gravity. And that force is going to be going directly downwards. And that is going to be force M, I'm going to call it. And I believe that in the previous slide, you had already stated that this force is going to be given by Newton's law. So it's going to be the mass that we are given. This is the 2 grams multiplied by gravity. And remember that we're talking about obviously international units, so we have to use grams. And gravity is a constant. So we're okay up to that point. And then we've got another force that's the string that's going this way. Okay. And I'm going to call that F. I'm going to call that the tension in the string. I'm going to call that Ft. Okay. And we know that this angle is 30 degrees. So if we divide if we divide this here down the middle and generate a right triangle, we know that the angle here is going to be, this angle here is 15 degrees. And so what is the angle over here? Can somebody tell me?
75.
75 degrees. Okay, correct. Got it. Thank you. 75 degrees. Okay. And so the force Ft has 2 components, the y component and the x component. And so the y component is going to be going this way, and I'm going to call it Fty. And then there's going to be an x component going this way. That's going to be Ftx. Okay. We know that Fty has to be equal to what? It has to be equal to Fm. And we also know that it is equal to Ft multiplied by the sine of 75 degrees. And we know that Ftx is going to be equal to, what is Ftx going to be equal to? Of the forces that we've written down there in the diagram. Can somebody tell me? The x component of this Ft has to be equal to what force?
To FQ.
Fq, correct, which is the
FQ.
To the Coulomb's law. And this in turn is equal to T multiplied by the cosine of 75 degrees. Okay. And so what I just want to verify here is just that the components were calculated correctly. Okay. The fx and fy components were calculated correctly in this case. So is this part clear to everybody? This breakdown? Now I'd like for us to go, I'm going to clear this. You can take a screenshot of this. I want us to go to the previous slide, Karen, please. Or whoever's controlling the PowerPoint, could you go to the previous slide, please? There we go. Ty is mass multiplied by gravity. So it's the mass. It's the mass here in grams multiplied by 9.81. Okay, 0.0196. Okay. And Tx is going to be, you've got Ty multiplied by the tangent of 15. Correct. And that gives you the 5.25 to the minus 3, and that is F. And then you're using it. Can you go to the next slide, please? And then you're substituting it here in the formula. Okay. So it seems the procedure is correct. Maybe sometimes some of these things are a bit sensible to decimals. So maybe if you use the 8.99, then maybe that would have given you something more closer to 1.2. That's what I'm thinking, because the solution should be 1.2. So I'm thinking it's the decimals because the procedure seems to be correct. Okay. The only thing I would recommend here in these problems, again, is to do the free body diagram. Okay. Please do the free body diagram just so we understand that where all of the forces are coming from. Okay. The rest of the procedure seems okay. So well done, Karen and the rest of the team. One question: why is it important for the problem to state that the two identical small spheres are fastened to the ends of a 0.6 meter long, light, flexible, insulating fishing line? Why is it important for the problem for them to tell us that they're hanging by a couple of long, tight, flexible, insulating fishing lines? Why is that important? For the sake of the problem. Anybody, give it a guess. It is important for the problem, but why specify that the spheres are connected by long, light, flexible, insulating fishing lines?
I guess that so that we can assume that it is a single line divided by 2.
Well, that's one good observation. So they're kind of connected. It kind of gives us the impression that this is some sort of hook, and this goes through here. So it's one line. Okay, good observation, Omar. What else? Again, why a long, light, flexible, insulating fishing line? Try to remember one of the first problem that Lucia explained about problem 1B that had to do with the charges that were touching each other. Why would it be important? Because this is a surface. Okay, this is a surface here. Why is it important that this connection or this line here be insulating?
Oh, so that it doesn't like steal electrons or something like that.
Correct, Mariana. So if this were any other type of material that wasn't insulating, then this connection here would make part of the charge go to the part of the charge go to the to this surface here. So the fact that it's a insulating fishing line, it means that there's a physical separation here with the material that is isolating the charges. So the charges are going to remain here in each of the spheres. If this line were of any other material that weren't insulating, then what happened in the previous problem, in problem B, would occur here also, where the charges would be divided. Or if we're thinking about a very large surface here, which then all of the charge would go there. Okay, so it's important for it to be isolated and insulated also. Okay. Okay. The long and light is very important because we're talking about it needs to have movement, so it's in equilibrium. Okay. Okay. Questions with this one before we move on to the next one? Are we okay up to this point?
Professor, I just have one question.
Yes,
So
please go ahead, Carmen.
we were right, or did we have to do that? What you explained?
Oh, your procedure is correct, Carmina. I was just trying to verify that you had done all of the considerations correct, because you should have gotten something more closer to 1.2. So your procedure seems to be correct. Maybe some of the decimals are affecting here. So maybe if you use the 8.99, maybe you would have gotten the 1.2. So the procedure is correct. The only observation I'm making, and I've done this for all of the teams, please try to do the free body diagram, okay? In the position where we're doing the analysis. That's the only thing. But the rest of the procedure seems correct.
Okay, thank you.
Okay, good. Okay, good. Let's go with our next problem, problem 10. And that we've got that one with House Ivana, please.
Yes, that's my problem. Okay, first we haven't uploaded it because we weren't sure of the answer, so we just want to check it out so we can upload it later. Okay. So it says that 3 negatively charged spheres is each with a charge of 4 times 10 to the 6 Coulomb are fixed at the vertices of an equilateral triangle whose sides are 20 centimeters long. Calculate the magnitude and direction of the net electric force on each sphere. And here I drew the triangle. It says that it's an equilateral triangle, so all the sides are going to be equal, the distance, and the charges are equal as well. And so we have the formula, and we basically substitute the values that we have. The two values are going to be the same, and the distance is going to be, we changed it to meters, and we got 3.59 newtons. And then in this part, we weren't sure why they used sine of 30 instead of 60, but we got the answer anyways. So I don't know if you could help us out explaining that part.
Yeah, let's
Professor.
Yes, go ahead.
In this one, there's a triangle. You have to get you have to do it like one by one and in 3 different formulas.
Well, let's do that, and let's see what's happening. So in general, Paulina, you follow the steps and the principles to be able to identify the magnitude of the forces. But again, and this is something if you notice, since we began, I've been mentioning to all teams, and I'm gonna say it again. And please do it from now on. Do the free body diagrams. Okay, you guys, all of you guys took a statics course and a dynamics course. So at least some takeaways from that is to do the free body diagram to identify the forces. So let me switch over here to my canvas so I can So I can explain a little bit about what's happening. I think in general, Paulina, the calculations are correct, but let's verify where the forces are and why certain angles are being used and others not, just so that part is clear, okay? Let me share now my screen, okay? And I'm gonna ask you to help me out with the values, okay? So we've got 3 charges, right? The charges are, do they tell us if the charges are positive or negative? Or they just say that the charges are the same?
Yes, no, they don't say if they're positive or negative. I mean, the number is positive, but I'm not sure if they meant it to be positive.
Okay, so let me just check that out quickly. We've got problem number 10. It says 3 negatively charged spheres, okay?
I'm sorry.
No, but it's fine actually, because right now the only thing we care about for the analysis is if the charges are the same or different. So we can identify the attraction or repulsion forces. I just want to be congruent with the colors I'm using, and that's just my OCD, because I believe I was using blue to represent negative charges and red to represent positive charges. So we've got 3 charges that form an equilateral triangle, okay? And that triangle, each side is how, what length, Paulina?
It's 20 centimeters long.
20 meters?
No, 20 centimeters long. It's
20 centimeters, so it's
0.2
meters. Okay. And the drawing of the problems and the visual representation is important for these problems, okay? And I find it very important for these problems to be clear, so you guys aren't necessarily just making calculations and putting stuff in formulas and really understand what's happening. Okay, so we've got an equilateral triangle. That's my version of an equilateral triangle, bear with me. And we know that if this is an equilateral triangle, what is the value of these angles here?
60.
60, perfect. So we've got 60 degrees. We've got 60 degrees. And we've got 60 degrees. And if that is 60 degrees, then we also know that there's a line that's separating this into 2 right triangles. And we know that this angle, therefore, is 30 degrees, right? Everybody okay up to this point?
Yes.
Questions? Okay, so we've got 30 degrees there. Now, I'm just for the purpose of the analysis, just for the purpose of the analysis, I'm going to call this one Q1. I'm going to call this one Q2. And I'm going to call this one Q3. And let's do the free body diagrams of each, because going back to Jose Carlos's question, the problem is stating that calculate the magnitude and direction of the net electric force on each sphere, okay? So technically we should be doing the analysis on each sphere. Now the spheres are the same values, so we should be able to make similar calculations, but it's important to identify how the forces are interacting in each case. So I'm going to do a free body diagram of this one here, okay? Q2. And remember, if you have any questions, stop me at any moment, okay? X. Don't have to put X and Y. This is a free body diagram. So I'm placed here at Q2, Is it clear to everybody that there's going to be a force between Q1 and Q2 that's going to be a repulsion force, and that force is going to be going in what direction? Can somebody tell me?
Outside, like the triangle outside.
It's going to be going this way to the right, and I'm going to call this F1, 2. Are we okay up to that point? We're also going to have another repulsion force between Q3 and Q2. And can somebody draw where that force is going to be going to? Go ahead and do it do it here. Can somebody draw? Just do a quick drawing. Where is the force between Q2 and Q3? Where is that going to be going to? Anybody, just jump in.
I think it's gonna be going up, but I don't know.
Well, put it in the free body diagram. Anybody, just draw it in the free body diagram.
It doesn't let me help. How do I draw?
I think just with annotate. You can do it, Paulina, or anybody that wants to give it a try. Go ahead. There's a option there in Zoom that says annotate, and then you can just select the colors. Or if you're having trouble with that, Paulina, anybody else? Where would the force be going to?
It would between Q3 and Q2.
Yes, Carmen.
Like up and a little bit to the left, like diagonal or something like that, or not?
Okay, can you draw it, Carmina?
Let me see.
Now, Carmina, and because Paulina also mentioned it, why would it be going up?
Because it's repelling, right?
Yeah, and so if Q2 is being repelled, is it going to go towards Q3?
Or maybe because there is just going up because there's equilibrium, or not?
No, there's not equilibrium.
Okay.
That's why we're calculating a net force.
Okay, so it will be like this or not? Something like that, or not?
I'm gonna ask you this. Where is the free body diagram? Is the free body diagram where you drew that, Carmina?
No.
Right now we're in Q2, okay?
Okay.
So where would it be with regards to Q2? We're in Q2 right now. That's where the free body diagram is.
Okay, like this?
Okay, that would mean that Q2 is going towards Q3, right?
Mm-hmm.
Won't the force go?
Oh, okay. So it will be like this.
Yes, correct.
Okay.
Very good, Carmina. Remember, and this, you guys, really, the calculations are important, but that's not the most important thing about these problems that I want you guys to learn about. We need to understand what's happening, and that's why the free body diagrams are important. So there is a force, okay, that is going downwards. Why is it going downwards? Because it's a repulsion force. So Q2 is going to want to go this way. And this is what were we going to call that? This is going to be F3, 2. Okay. And what is the angle here between X and that force? Can somebody tell me? Anybody?
What is it?
What is the angle here?
60.
60.
No. Yeah, 60, right?
60. Okay. So how do I calculate the net force? Well, I need to calculate the components. Okay. So to calculate the components, I'm going to calculate F. The component in X is going to be F1, 2 plus F F32 multiplied by the cosine of 60. And I also need to calculate the y component. The y component is going to be, what is the y component going to be in this case? Anybody? So the x component is going to be F12, and the x component of this one, what is the y component of the resultant force going to be here?
The F32 negative.
Okay, again, could you repeat that, Omar?
The force 32 in a negative way.
Just F32 by itself? We're talking about the y component.
Professor, but why is it gonna be negative?
Because it's going down.
Oh, okay.
So that's why the free diagram is important. Because we want to look at what's happening with regards to the forces and where they're going, okay? So we're able to really, in this case where there's a net force, we're able to identify where the net force is going. So in this case, the signs of the forces are important. So when we draw the free diagram, we take the a convention for the free diagram. We're going to say an XY Cartesian plane, right is positive, up is positive. Down is negative, left is negative. But is it just going to be F32, Omar?
I think so.
But F32 is the purple line. We're looking for the blue line. So what is the y component of F32?
Professor, don't you have to multiply that by sine of 60?
Oh, sine of 60.
That's
Sine of 60,
don't get angry with me, Lucia. That's what I was getting at with
I'm angry.
I'm joking. Remember, this is my humor that I only find funny. That's what I was getting at, Lucia.
I was thinking, and it came like out so
No,
proud
that's fine.
because
I think Lucia wants to be in the waiting room for a while.
No, that's fine. That's fine.
Professor,
It's not that I don't remember these things or I don't know these problems. I'm trying to get you guys to answer.
Then they
Yes.
always have to put me in the waiting room. I think it's his turn.
No, yeah, we're gonna put everybody in the waiting room. No,
Lucia wants to finish the program by herself.
no. Okay, so I'm sorry about that, Lucia. I was joking. So yes, it's correct. The y component is going to be the sine F32 multiplied by the sine of 60. Okay, and the total net force F is going to be the square root of Fx squared plus Fy squared. And what angle is that net force going to have? That net force is going to have an angle of, or is going to have an angle that's given by the inverse tangent of Fy divided by Fx. Now, let's do I'm going to need the help of you guys with the calculations, please. And team Paulina and company, you did the calculations, so you'll be able to give me the values. But F12 is basically given by Coulomb's law, K Q1 Q2 divided by R squared. We know that Q1 and Q2 have the same value, so you should have been able to calculate this. What is the value of F12? Which is K Q1 Q2 divided by R squared. You should have calculated that one?
Yes. Let me do it again because I don't have that.
And this is actually going to be the same magnitude of F32. Because F32 is also, the only difference is that F32 is going to be Q2. Let me just write this down and I'll write down the answer. The only difference is that
value on top.
yeah, give me a moment, Paulina, please. F32 is going to be KQ2 Q3 divided by R squared, but all of the values are the same. So what is the value of this force now, Paulina?
It's gonna be 3.59.
And that's the calculation with the values, right?
Yes, that's the final result of that part of the formula.
Okay, could you repeat that? 3.59?
59, yes.
Newtons?
Yes.
Okay. 3.59 newtons, okay? And again, Paulina, just to be clear, because I'm not doing the calculations here, this value that you just gave me of 3.59 or rounded up to 3.6 is K Q1 Q2 divided by R squared, which would mean K multiplied by the values of the charges divided by R squared, which is 0.2 meters to the square. It's just that value, right?
Yes.
Perfect.
That's right.
Now, please calculate fx. And fx is going to be f12 plus f32, which is the same value multiplied by cosine of 60. You can do it, Paulina, or anybody that could help out with that calculation, please.
Yes, but in that part, I just wrote 3.5 times sine of 30. Like, I don't know why you wrote an addition. Like, what do you need to add?
Well, look at the free body diagram. What are the forces that are in X in the free body diagram? How many forces are in X?
2.
2. It's F12, which is along the X-axis, and the X component of F32, which you can represent that either way. You can represent that as F32 multiplied by the cosine of 60, like I did it, or you could also do it F32 multiplied by the sine of 30. Either of those could give you the value, but you need to add both components, okay? Both of these components are the force in X, okay? Not only this one. Both of them are acting in X. Is that clear?
Kind of. I hate body diagrams. I never understand them. I mean, I get it, but like I'm confused.
Well, okay, and it's part of what we need to kind of refresh for these problems. So the first thing that's it's very important for to be clear for everybody. Is it clear that there's a force between Q1 and Q2 that's going to the right, I'm sorry, along the x-axis? Paulina, so is this force here clear? Right. And then we go between Q3 and Q2, there's another force that's going downwards, which is this one, that's going in this direction, right? Is that clear also?
Yes.
Now, the way a free body diagram works, just to remember that, is that the total force is going to be given always in 2 dimensions by 2 components, the x component and the y component, okay? So to understand how a free body diagram works, you look at the free body diagram, and first, Paulina, we're going to look at the x's, and the x's is the horizontal, okay?
Okay.
So let's look at the x's. I'm going to look at force 1, 2. Force 1, 2 is along the x-axis, right? So that's one of the components that we have. And then when there's a force like force 3, 2, which is the one that's going down at an inclination, force 3, 2, since it is at an inclination, is going to have 2 components, the x component and the y component. How do we calculate the x component of this one? Well, it's always going to be the magnitude multiplied by the cosine of the angle. And in this case, it's the angle that's with regards to x. Okay. And so those two are going to add up.
Oh,
Okay.
okay, but it's the same, like the force is gonna be the same, 3.5.
Yes, the magnitude is going to be the same
The
force.
magnitude.
Yes, yes. So it's going to be 3.5 plus 3.5 multiplied by cosine of 60. Okay.
Mhm.
Can you give me that, or anybody? Can you give me? Can anybody give me that value, please, if you can calculate it?
It gives me 3.5, the same, but I don't know if I
Maybe there's
3.5 plus 3.5.
multiplied by the. Remember to multiply the cosine, and remember that the value has to be in degrees.
I got 5.38.
5.3. Can you repeat that, Omar, please?
Yes. 5.38.
5.38, and these are newtons, right? Okay. And now let's look at the y-axis. Now, looking at the free body diagram, what is the only force that has a y-axis component? F32. What is that y-axis component going to be? It's going to be F32 multiplied by the sine of 60, but it's going downwards. Okay, so Fy, can somebody do this calculation, please? F32, which is 3.59 multiplied by sine of 60.
Is it 3.10? I don't know if my calculator is, but I did it and it gave me that.
Okay, 3.10. Can somebody verify that?
Yes, that is correct.
3.10.
Yeah, that
newtons.
is correct. Or 2.3.
That is correct.
Okay, 3.10 newtons or 3.1 newtons. Let's just finish this up, and we'll leave. Okay, just so the complete problem is in the recording. Now, please calculate the value of F. The total net force is going to be the sum of these components, the square root fx squared plus fy squared, square root of that. Can somebody calculate that, please? And that should be the result that we're given in the problem, which is 5.38 times 5.38.
Is it 1.5?
Okay, can somebody please verify that, please?
15.
Oh,
I got 15.
I think you have your calculator in radians.
Maybe it's in radians. Yeah. Can anybody repeat the value again? 1.16. Could you repeat that again, Omar? It got cut off.
15.
1.15. Newtons also?
No, 15. Like.
Oh,
Newtons.
just 15?
But it's only 15 newtons. Yeah.
Professor, I got 6.20. I don't know why.
Yeah, it can't be 15 newtons because the two forces are smaller than one is 5.38 and the other one is 3.1. So the resulting force can't be 15. It should be fx squared, which is 5.38 times 5.38. That's 28.9. And fy is 3.1.
Yes, Marisa is correct. It is 6.2.
Yes, I got the
6.2.
same.
Okay, 6.2 newtons.
Same.
Okay. And lastly, before we go, just to calculate the angle is going to be the inverse tangent of fy divided by fx. And remember to use the sign. So it's minus 3.1 divided by 5.38. And the inverse tangent of that. And remember to have them in degrees, please.
I got a negative 29.9.
Negative 29.
right? 29.9.
Yeah, I got that too. 0.95.
29.9, which is roughly 30, approximately 30 degrees. So that would
Yes.
mean that the resulting force is going something like this. The resulting force is going this way with a negative angle, which is theta, and a magnitude of 6.2. Okay, so that is the resulting force. Okay, we're going to break down the analysis on the other two. The magnitudes of the other forces should be the same. The only difference is the directions they're going. Okay, so I'm going to take a screenshot of this so we can continue with this problem next session. Okay. Okay, I'm going to stop recording